Thank you very much. I'm Sanjin. I will present this paper. I'm coming from University of Rijeka, also from Croatia, and Faculty of Engineering. This is the presentation. It is mostly about vibration models and how they impact the fatigue assessment. So the International Maritime Organization has mandated that carbon dioxide emission should be greatly reduced. So for all ships, it means that they need to go to sail slowly, and for new to install smaller engines. Considering classification organization, they recommend that mostly critical is torsional stresses and in some cases flexural stresses. This research is about investigation how these flexural stresses could maybe impact or decrease the fatigue life. And the focus is intermediate shaft of the marine shaft line. Traditionally, shaft lines are considered as driven by axial excitation and consequentially stresses, also torsional and bending, where the torsional stresses are considered the most critical. This is the most simple torsional model, and the first flexural mode shape look like this. In real ship, it is rather more complex model, and here is a shaft line and a lot of influential parameters. If we apply finite elements, we can use two different approaches with lumped mass or with distributed mass. The simplest approach is with lumped mass, where masses are considered rigid, and the shaft elements could be replaced by springs. Considering engine data, this is the most the hardest part of this investigation, to find the data for the engines. And in this case, 8.5 megawatt engine is used, and it has 5 cylinders. Three different approaches are applied, considering two open source softwares to be applied in Python and ANSYS as well. So the first is torsional, open torsion, developed by Aalto University of Helsinki, and it offers only torsional vibration. ANSYS could do everything, but some difficulties could arise considering additional masses and additional dampings, and also from Brazil, Petrobras, they developed ROS, Rotterdamic open source software. Comparison of their result show very good agreement. it must be pointed out that different approaches are considered with lumped and distributed mass. Roche basically used distributed mass. ANSYS as well, but if you took density 0, then you can use only lumped mass with no distributed mass. And open torsion uses lumped mass approach. These are excitation function and also excitation from the propeller. Steady state response at a maximum continuous rating is presented here, and considering Detnorske Veritas guideline, this is enough to assess the fatigue life of shaft line. And these are responses, torsional stress responses for each particular shaft element, sorry. So, advantages and disadvantages. Open torsion didn't have transient analysis at the beginning, but we included. So now it has. ANSYS has everything, but some possible problems with adding additional mass and damping matrices. And Roche has everything prepared for flexural analysis, but they left compatibility for 6 degrees of freedom, but with only compatibility on some level. So it needs to program additionally. And specialized program from DNV, Nauticus torsional vibration, has everything, but not functionality of transient analysis, and don't have coupled torsional bending analysis. Just to see what it needs to be done for transient analysis. If you want to obtain stresses at the end, in this case, we assumed that the ship is running somewhat below bare speed range, and that it needs 3 seconds to accelerate above bare speed range. Bare speed range is like a resonance region which should be passed very quickly. So these are engine excitation function and the propeller excitation function, and these are stress response at the intermediate shaft. These steps, some of them are already done, some need to be done. So in all 3 softwares, torsional analysis is performed, and comparison is provided. Transient analysis is possible in ANSYS and open torsion, and in ROS should be programmed additionally. The idea is to continue with ROS and ANSYS parallelly to verify each other, by the way, on the fly. The idea is to include the mass and damping matrices at the propeller position, and it will be the position where this coupling between the torsion and flexural analysis will be done. So matrices of added mass and of added damping. looks like this. Also, propeller excitation are included, and the propeller as well. And considering fatigue analysis, DNV and other classification societies, they recommend focusing on torsional stresses. Our idea is to include flexural stresses as well. So, torsional vibration impact the low cycle fatigue. If we want to include bending, we need to consider it at the high cycle level. And special attention, especially for slow steaming ships, should be paid to bare speed range or analysis, transient analysis when passing to this bare speed range. So, with the result of whole shaft line, the result are inputs for the detailed intermediate shaft part. So here you can see that the shaft is fixed here and excited on this part, and these are a result of the stresses. If we include additionally the lateral forces, vibratory forces, we see some small increase in the stress level, some 5 megapascals or 5%. And here we see the critical region considering the life. And with this biaxiality indicator, we see that the stresses are mostly shear stresses, and with some deviation to the normal stresses. So biaxiality should be 1. Okay, I'm almost finished. I try to present our approach where we want to include the coupled torsional flexural analysis in order to investigate how they impact the possible increase or decrease of fatigue life of intermediate shaft of the cargo container ships. Thank you very much.